ろしくお願いいたします。Good afternoon. こんにちは。私は李愛萱です。彼は陳燕婷です。彼は曹丽慧です。Okay. We are from Zhong Senior High School, which is located in Taipei, Taiwan, and our research is systematic in numeration of simple organic compounds. Okay, about the motivation is from dimethylbenzene, which is our chemistry teacher mentioned in the class. Take the substituents are all hydrogen atoms of, for example, it has 3 isomers, 1, 2, 3. We can't help but wonder that if we change its substituents as with A, B, C, D, E, F, and how many isomers would there be? We also find some references, but they solve the problem of isomers with generating function, and their substituents are irreplaceable. So the following are several proposed to calculate the number of isomers of alkene, cycloalkene, and cycloproene. Take this one structure for example. This is a planar structure, and we number the positions 1, 2, 3, 4. If we have I choices on every position, then we will have I, the first power of I, different structures. So we call them configurations. These configurations can be classed into a configuration set S. But some configurations can turn back to the same configurations by some permutation actions. For difficult chemical materials, such as some planar structures and 3-dimensional structures, we can find out their symmetry axes and symmetry planes describe the rotation and flips in mathematical cycle, like this. And we collect these actions as a permutation group G, like this. So we can just let permutation group G on configuration set S and set S. Permutation group G can be separated into several equivalent classes. So the number of equivalent classes is our isomers number. And this is the simple chart.
In this page, we take methane for example. Its carbon can be connected to 4 substituents. We first list its 12 actions, and according to Burnside lemma, we can find the number of isomers of methane. In this page, we discuss the number of isomers of alkane. Take C4H7CO3 for example. We first discuss the both ends of carbon structures, like this. We can find the 9 cases. The first example is type XXX and type XXX. The second example is type XXX and type YYY. And so we can find these 9 cases. Then we list the remaining substituents, and according to Burnside's lemma, we can find the number of isomers in 9 cases respectively. Finally, we add the number of these 9 cases together to get the total number of these isomers.
According to Burnside's lemma, let G act on S. We can, for all actions G, then we can get SG for every action G. We calculate the summation of the order of SG, then divided the summation by the order of G. It is the number of equivalent class, and it is also the number of isomers. And here is the cycloalkanes isomers formula. The first part is about rotations. The second part is about flips. Similarly, we can obtain the isomers formula of cyclopolene. This is even number of conjugate range structure, and this is other number of conjugated range structure.
And this is the process we sort out. A to F. A, for given carbon atom numbers and substituents for stations, drop all possible structures. Fill in 3 substituents in every endpoint of a structure, respectively, and discuss the possibility of optical isomers. C, give number for every position. If there are 3 substituents on 1 carbon atom, then we give only 1 number for them. D, find out all possible actions of a structure and set the actions in mathematical cycles. E, use Burnside's lemma to calculate the number of isomers of a structure. F, we can repeat step A to E for every possible structure of the given molecular. Finally, we can get the total. So, for example, we take this molecular C4H4F2CO2, for example, and you can sum every structures, and you can get the total isomers of that molecular. Conclusions and future works. Develop a simple and an efficient methodology to calculate the number of isomers of single organic compounds. 2. For given numbers of carbon atoms and substituents, we find all possible actions combined with the group theory, that is Burnside's lemma, and turn it into permutation group based on the the analysis of its structure. Then we use Burnside's lemma to calculate the number of isomers with linear permutation on cycles of elements in group. We also write Python programs to describe the formulas listed in our study. Finally, in the future, we hope to employ the methodology on polymer or biomolecular with more complicated structures. Thank you for your listening.
ありがとうございました。それでは質問をお受けしたいと思います。質疑応答のお時間です。どうぞ高校生の皆さんもよかったら手を挙げてください。ご質問のある方いらっしゃいますでしょうか。ご質問はいかがでしょうか。一番後ろの方にではお願いします。
Thank you very much. So in your strategy, of course it's important to consider the symmetry, right? Especially in the cyclic system, it has a cis and trans isomers. So I couldn't follow the details, but do you consider such symmetry of compounds?
Can you say it again and more slowly? Can you
More slowly.
say it again?
In your strategy,
Yeah.
it's important to consider the symmetry of the compounds,
Yeah.
right? Because
Yeah.
you count isomers, right? Then, especially in cyclic system of compounds, of course, as you know, it's important to consider cis and trans isomers or ring symmetry, also everyone. So because I couldn't follow the detailed equation, so did you consider appropriately? Could you please again explain how to consider the symmetry?
Oh, and like this.
In cyclic system especially.
Oh. We find all of its symmetry actions and write into cycle. For example, this is identity if you don't move, then if 1, 2, 3, 4. But if you rotate 90 degrees, and will be 1 to 2 and 2 to 3 and 3 to 4. So 1, 2, 3, 4. And this is rotate 180 degrees. So 1 turn to 3 and 2 to 4. So 1, 2, 3 and 2 to 4. So we use this to collect to consider all of its actions and write into math formula. So use Burnside's lemma. This is a lemma of this group theory. So we can write into this lift and rotate and flip. Rotation and flip.
Thank you. Thank you very much.
ありがとうございました。それではお時間も参りましたので以上とさせていただきます。ジョンハーシュニアハイスクールの皆さんでした。ありがとうございました。